Okay, hello everyone. Good morning, all of you. So we'll start with a quote by Lao Tzu. So he's a Jain philosopher, and he says, "Be content with what you have. Rejoice in the way things are. When you realize there is nothing lacking, the whole world belongs to you." Okay, actually, the richness of a person depends on how much he is satisfied. Whatever they have, even if a person has crores of rupees and if he is not happy, he is considered to be a poor person only. And without having anything, if he is happy, he is equal to a rich person. Okay, and today is the birthday of Johnstone Stoney, and he was an Irish physicist who coined the term electron for the fundamental unit of electricity. At the Belfast meeting of the British Association in August 1874, in a paper on the physical units of nature, Stoney called attention to a minimum quantity of electricity. He wrote, "I shall express Faraday's law in the following terms. For each chemical bond which is ruptured within an electrolyte, a certain quantity of electricity traverses the electrolyte, which is the same in all cases." And he subsequently offered the name electron for the minimum electric charge. When Thomson identified cathode rays as streams of negative particles, each carrying probably Stoney's minimum quantity of charge, the name was applied to the particle rather than the quantity of charge. Okay, that is the way, and he is the first person named or coined the name electron. Okay, today we will discuss nonlinear problems, but before we go to that, so we will see some revision of the last class. So we have discussed about splitting methods and multidimensional problems. So we have seen that why we go for splitting methods is if we have multidimensional problem, and if we go for explicit methods, the condition for stability will be making the delta t very narrow and small. So that's why normally we don't prefer. And if you go for implicit methods, it is going to result with, for two-dimensional problem, pentadiagonal matrix, and for three-dimensional problem, heptadiagonal matrix. So which is complicated in solving and takes more time. And because of that, we go for splitting methods, which are mainly ADI method, alternate direction implicit method, or approximate factorization of Crank-Nicolson. And the other one is fractional step method. Okay, these two methods are called as splitting methods. So they are meant for multidimensional problems. So the other problems, schemes which are called as multi-step methods, which are also called as predictor corrector methods, they are meant for nonlinear problems. Okay, so you have to distinguish between splitting method and multi-step method. So there also the time is split, and here multi-step method also time is split. But these are not called as splitting methods. They are called as predictor corrector methods. In the predictor step, we predict an approximate value and then we correct it in the second step. Okay, there are two-step methods. Then some of the multi-step methods we have discussed are Meyer method. So the main specialty of Meyer method is its condition for stability is C less than or equal to 2. And for all of them, others C less than or equal to 1. And the other one is a two-step Lax-Weintraub method, and then McCormack method. So there is more importance for McCormack method, and it is widely used, as I told, because in predictor we use forward difference, in corrector backward difference, or vice versa. And when we use that, any type of flow can be solved. Because normally if it is going from left to right, we prefer upwinding, or if diffusion is dominant, we use a central difference, or if it is right to left, we use forward difference. And here, because the flow can be any direction, and so McCormack method can be applied without any problem of stability, and it is widely used. And then we have seen application problems for linear hyperbolic solver. So we have taken one application problem and we have seen how each works. And when we have seen the solution, the one thing we have discussed is about the error. So sometimes we have dissipation error and sometimes we have dispersion error. And the schemes which are of first order accurate schemes, they have dissipation error because the term which has the dominant error term is of second order derivative, and which works like a diffusive term or dissipation term or viscous term. And because of that, whenever there is a sharp gradient is there, it gets diffused and it gets rounded off, or it gets smoothed, or it gets smoothened. Okay, so that's what happened with first order accurate schemes with the second order derivative in the dominant error term. And the second order accurate schemes where third order derivative is the dominant term, there is what is called as dispersion error will come into picture, due to which there will be oscillations whenever there are sharp gradients are present. And this is a bit dangerous. Dissipation error, though the error may be more, but the scheme works well. But dispersion error, when the oscillations are large, sometimes it will be too much, and sometimes it may go to negative values which are impossible, like density may become negative, which is impossible. So such things may happen. And so when the dispersion errors are very large, because here what happens is I want second order accurate scheme, but dispersion error will come. And keeping dispersion error order accuracy, and if I want to suppress the dispersion error, I have to sometimes artificially include numerical dissipation, like adding some fourth order derivative. So those things we will discuss today. First, we will discuss about error analysis. Okay, so the errors associated with first order accurate methods are known as dissipation errors or diffusion errors. These errors tend to decrease the gradients within the solution domain. So like this, actually this decreases the amplitude and sharpen the rounds of the sharp corners. Okay, and the errors associated with second order accurate methods are known as dispersion errors. So dispersion errors, dissipation error produced by a first order accurate method is indicated by a decrease in the amplitude in the wave, while the dispersion error creates in the second order accurate method is indicated by oscillations in the solution wherever there are gradients. Okay, so we will see some examples how to get the error.
Sir, yesterday you asked the relation between implicit damping and explicit damping coefficients, sir.
Yeah, we will discuss.
Okay.
Okay, we'll so we have the equation, and we take output. So we uin plus 1 minus uin by delta t is equal to minus a ui minus ui minus 1n by delta x. Means uin plus 1 minus uin is equal to minus c into uin minus ui minus 1. Okay, so here we get what is called as modified equation. So modified equation means substitute Taylor series expansions in the finite difference scheme. Okay, this is the first step. So that is what we have done to get the consistency. So like that, we have to uin plus 1 and ui minus 1, and there I have to substitute the Taylor series expansions. And then replace time derivatives with the space derivatives. Okay, how we do it? So we have ut is equal to minus aux. So wherever ut is there, substitute minus aux. And if I have utt, we know that we get a square uxx. that is second order wave equation, by differentiating it with respect to t. And again, if you differentiate, you will get UTTT is equal to, can you tell me what is that we get? Anybody? Differentiate this again with respect to t. Okay. So here again, xx you take out and t you take in. So ut is equal to minus ux. So it will become minus a cube uxx, like this. So in this way, you have to replace the time derivatives by x derivatives. So if you do that, we are going to get what is called as modified equation. So in the modified equation, check the largest error term. So the behavior of the scheme depends on that. Okay, so we'll try to do that. So we are taking upwinding. So ui n plus 1 minus ui n equal to c into ui n minus ui minus 1. So if I substitute ui n plus 1, I will get ui n plus delta t ut plus delta t whole square by factorial to utt plus delta t whole cube by factorial 3 uttt minus, okay, this is the expansion plus etc. minus uin, that is the left hand side. On the right hand side, minus c into uin minus of ui minus 1n will become uin minus delta x ux plus delta x whole square by factorial 2 uxx minus delta x whole cube by factorial 3 uxxx plus etc. So like this you will get. So on the left hand side, uin gets cancelled. On the right hand side also uin gets cancelled. And this minus c, I will write it as a delta t by delta x. Okay, so delta t on both sides I will calculate cancel. Delta t this goes off, this delta t goes off, one delta t goes off here, and delta t whole square it will be. And on the right side, I divide by delta x. So delta x goes off here, delta x goes off here, one delta x. Like this it will be. Okay, so what is that I'm going to get on the left side? I have ut plus delta t whole square by 2. And what is it? Yes?
Only delta t.
Yeah.
Not delta t whole square.
Yeah, delta t whole square by 2. UTT is square uxx. Okay, plus.
Sir, it's not delta t whole square, it's just delta t.
Yeah, only one delta t. Right, thank you. Yeah, thank you. So delta t by 2 a square uxx. And next term, I will not take it because uxx is the biggest error term. Uttt I will not take, etc. I will put is equal to, on the right side, I'm going to get a minus aux because 3 negatives are there, 2 negatives will go off, and minus auxx, and next aux. So this term will be there. So delta x by 2. So how many minus 2? So plus a, sorry. Okay, uxx, a delta x
by 2 factorial.
By 2 factorial. Okay, and plus etc. So ut plus a minus aux, these two will be the terms which are needed. These are the two error terms. I will take to the other side, this axx. So ut is equal to minus aux plus uxx I take common. I'm going to get minus a square delta t by 2 plus a delta x by 2, like this. And so this is the error term. And I will write this as uxx. A delta x by 2 I take common. So that will be 1 minus a square, a delta t by delta x I will get. Okay, this is the error term. Or a delta x by 2 into 1 minus c uxx. Okay, this is the error term. And usually, if you remember, we will have mu dou square u by dou x square, dou square u by dou y square, like that for the diffusion term or the viscous term. So this here, dou square u by dou x square is there, and this works like viscosity. So that's why this is called as mu a, or artificial viscosity. So this particular term uses like works like a viscosity, though it is inviscid flow. Basically, the fluid I am taking inviscid flow, but without knowing, because of numerical error, truncation error, it acts as if it is viscous. So wherever there is sharp gradients, it gets diffused, it gets smeared, and shocks get smeared, and so the sharp gradients gets rounded off. All these things happen because of this. Is this clear?
Sir, I have one question, sir.
Yes. Ask.
Sir, our original equation is ut is equal to minus aux, right?
Yeah, but I am solving this. Ut is equal to minus aux plus this. Okay, this particular equation I am solving. Though I want to solve the ut equal to minus ux only, I have to solve, but I am solving this.
Okay. The discretization error that is coming from the usage of the Taylor series.
Finite difference scheme introduces this particular term into that. So it acts like a viscous flow.
Sir, the whole coefficient is artificial viscosity.
It is small only, but though this is small, the errors are small, but the effect of this is the sharp gradients gets smoothened out.
Okay. Whole term is artificial viscosity, sir. Only 1 minus is artificial viscosity.
A delta x by 2 into 1 minus c is the artificial viscosity.
Okay, sir.
Okay, that is the coefficient of dou square u by dou x square. Okay, so this is first order accurate scheme.
So, sir, when current number is 1, that's why artificial viscosity is 0. So that's why you get accurate scheme.
That error will be 0.
Yeah, fine.
Yeah, that's why it gives better distribution. Okay, next we will see second order accurate scheme. So we take CTCS, or midpoint leapfrog scheme. And so here, if ut is equal to minus ux in, so I take ui n plus 1 minus ui, CTCS means ui n minus 1 by 2 delta t is equal to minus a ui plus 1 minus ui minus 1 n by 2 delta x, like this. So this 2 goes off. So you will get ui n plus 1 minus ui n minus 1 minus c to ui plus 1 n minus ui, like this. So if I again substitute these expansions, so it will become ui n plus delta t ut plus delta t whole square by factorial 2 plus delta t whole cube by factorial 3 utt plus etc. minus uin minus delta t ut plus delta t whole square by 2 utt minus delta t whole cube by factorial 3 uttt. This is on the left side is equal to minus c is minus a delta t by delta x into uin plus delta x ux plus delta x whole square by 2 uxx plus delta x whole cube by factorial 3 minus uin minus delta x ux plus delta x whole square by 2 uxx minus delta x whole cube by factorial 3 uxxx. Okay, like this I will get. And here uin gets cancelled, uin gets cancelled. And here delta t whole square by 2 utt, delta t whole square by 2 utt gets cancelled. And here on the right side, delta x whole square by 2 uxx and delta x whole square by 2 this uxx because minus is there. Okay, so and delta t, if I cancel on both sides, this delta t, and this will become whole square. This delta t goes off, this will become square. And delta x, if I cancel, here delta x goes off, here delta x whole square, here delta x goes off, here delta x whole square will be there. So you will be left with ut plus 2 times this will be there, delta t whole square by factorial 3, 2 times uttt. Uttt is a cube uxxx minus. Okay, it will be there like that on the left side. On the right side, minus a ux, 2 times will be there, 2a ux. And this also 2 ut will be there. And again, this third order derivative will be there. This is plus or minus? Minus only 2 delta x whole square by 6 uxx. Like this it will be there. Okay, so 2 if I cancel, 2, 2, 2, 2. So ut is equal to minus a ux. And here uxxx, if I take common, so left side it will come, it becomes positive. So a cube delta t whole square by 6. And in the right side minus delta x whole square by 6. Will there be, a will be there, right?
Yes, A will be there.
A will be there, right? So now, so this is the error term, which is having third order derivative. And the coefficient, if I take a delta x whole square by 6 common, it will be minus that side will be there, a square delta t whole square by delta x whole square minus 1 will be there. Or a delta x whole square by 6 into c square minus 1. Okay, this is the coefficient. Okay, this is not having any particular name like viscosity, but this is the error term. Okay, into uxx. Because this is third order derivative, this brings out dispersion error. It is just to show that if I take a second order accurate scheme, usually the dominant error term will contain third order derivative, and it introduces dispersion error, which creates oscillations wherever there are sharp gradients. Okay, so this is important. Any questions in this? Is it okay, the derivation?
Clear, sir.
Yeah.
Yesterday, I actually did a shock simulation. There, I tried second and third order. Third order was giving accurate, like without any oscillations. Now I know the reason.
Second order, that's what first order accurate, third order accurate, it will introduces dissipation. Because of that, there will not be instabilities or
Convergence is better in third order.
Yeah. Okay, so this is modified equation and FTB a subprint scheme. Okay, this is the error term here. And so the dominant error term contains second order derivative representing dissipation error, and the coefficient of Uxx represents artificial viscosity. And the modified equation for midpoint leapfrog. So we are going to get this A delta x whole square by 6 into C square minus 1 into third order derivative. So the dominant error term contains third order derivative represent dispersion error. Okay, so this is like this. You can find out the error term for any type of scheme. So only thing to understand is if there is second order derivative or fourth order derivative in the dominant error term, it creates diffusion. Okay. Okay, so here we take nonlinear hyperbolic solvers. Last class I was telling ut is equal to minus ux if I take. So this is written as dou by dou x of u square by 2. This u square by 2, if I write it as e, then dou u by dou t equal to minus dou e by dou x. So this is the equation. And okay, if there is a wave like this, a step function, okay, it's a step wave. So where the velocity is given by u of x0 is equal to 1, 0 to 2. So here x is varying from 0 to 4. 0 to 2, the velocity is 1, and 22 to 4, the velocity is 0. So u of x0 is equal to 1, 0 to 2, and u of x0 is equal to 0, 2 to 4. Okay, so this is the initial condition. Initially, this wave is there, and then I have to march in time using the discretizing this. So this dou u by dou t equal to minus dou u by dou x. This is done by various methods, like Lax method if I take. Okay, so first I have to write FTCS, and after writing FTCS, this UIN is to be replaced by average of the neighboring points. So that is ui plus 1n plus ui minus 1n by 2. Okay, this is the way. And this is central difference. We write like this. And here E is there, but E is u square by 2. So I have to substitute u square by 2. So here you understand, okay, though it is nonlinear, u square is nonlinear because I am taking at n, which is already known value. Square of a known value, no problem. I should not take square of unknown value. If I take implicit method, then there will be problem. I have to get right ui plus 1 n plus 1 whole square, then that will be nonlinear. Okay, so writing like this, it is explicit method, and all are known values on the right hand side, only one unknown on the left hand side. Okay, so this is the way I can solve the equation. This is using Lax method. And so if I march in time, initially this is the wave, and gradually as the time increases, the wave propagates like this. And so because of the errors, so you are going to get not a sharp one, but they are rounded off. Okay, and the condition for stability, usually current number A delta x by delta t, sorry, A delta t by delta x. This is wrong. Okay, I typed wrong. Okay, so this should be less than or equal to 1, but here there is no A here, right? Because it is nonlinear equation. So I have to take u max. And order of accuracy delta t delta x whole square. Okay, and so when c equal to if c equal to 1, the error will be less, and if c equal to 0.5, the error will be more. Okay, so c equal to 1, it's almost like a bit sharp only, but c equal to 0.5, it is changing like this. This is Lax method. And if you come to Lax-Wendroff method, so Lax-Wendroff method, what we do, we take this expression uin plus 1, Taylor series expansion, uin plus ut delta t, and dou by delta t whole square by 2 utt. So this ut and utt, I have to substitute from the original equation. And ut is minus ex, so that I am writing here. And utt, so what I have to do, utt is equal to just like wave, second order wave equation. What I do, dou by dou t of dou e by dou x, and x and t I interchange. So dou by dou x of dou e by dou t. And here there is important thing. This dou e by dou t, I write it as dou e by dou u into dou e by dou u by dou t. This dou e by dou t is written as dou e by dou u into dou u by dou t. Okay, this is a particularly important thing. This is called as Jacobian derivative of flux with respect to dependent variable. Okay, this is very important. Later we will come across this when I have simultaneous equations. It is going to be a matrix. Okay, so derivative of a dependent matrix, the flux matrix with dependent variable matrix. So if you remember, we got dou u by dou t plus dou e by dou x plus dou f by dou y plus dou z by dou z is equal to j. Like this, we got the general all simultaneous equations together, right? So U is where U is solution matrix, and E, F, G are flux matrices. So if I take dou E by dou U, this is what is called as Jacobian. Okay, so this we will discuss in detail when you go to incompressible Navier-Stokes equations. But for the time being, just you take it like this. So dou E by dou U, which is a Jacobian, we write it as A, capital A or capital B, like that. Okay. So here, dou square U by dou T square, which is dou by dou T of dou E by dou X, right? And this dou E by dou X, this X and T I interchange. So it will become dou by dou X of dou E by dou T. This dou E by dou T, I will write it as dou E by dou U into dou U by dou T. This dou E by dou U is Jacobian A, and this dou U by dou T is again, I substitute minus dou E by dou X. So this will become minus A dou E by dou X. And this particular one is substituted here in this equation where I have UTT, because this UIN plus 1 is UIN plus UT delta T plus UTT delta T whole square by factorial 2. This I will substitute here. And for this particular single equation, it's no problem. You can find out this. So A is dou E by dou U. U is U square by 2. E is U square by 2. So dou by dou U of half U square. This is U is 2U. 2 gets cancelled, and U only is Jacobian. Okay, here it is very simple. Capital A is U only. But when you have simultaneous equations, it is going to be a matrix, and it's a bit complicated. But here it is just, though I write A here, nothing to worry about it. It is just U only. Okay, but here continue with A dou E by dou X here. Okay, so in Lax manner of what we do, we write the X derivatives, and after that we write them in central difference form. So dou E by dou X is written as EI plus 1 minus EI minus 1 n by 2 delta X. And this A dou E by dou X, so here A dou E by dou X I plus half, A dou E by dou X I minus half by delta X. We will take the central difference this way. So why I am taking like this is because another X derivative is there. When I take central difference for that, I am going to get I plus 1 and I. And for I minus 1, I and I minus 1 are the left and right hand sides. Okay, so for that purpose, we are taking like that. So when I take this A dou E by dou X I plus half n minus A dou E by dou X I minus half n. So this is A I plus half into dou E by dou X I plus half. So A I plus half, how can I get A I plus half at I plus half? I take average of I and I plus 1. So this is like AI plus 1n plus AIN by delta by 2. Okay, average of these two. And dou E by dou X at I plus half, I have to take the central difference. So we will take EI plus 1 minus EI by delta X. So that is the way we write, and I get the whole equation this way. Okay, so this is the Lax-Ventropf scheme. We get like this. And if I do the solution of the same equation using Lax-Ventropf, we are going to get like this. So as time progresses, right, the wave moves in this way, and there is a little bit of oscillation here because Lax-Ventropf is second order accurate scheme. And so if I take c equal to 1 and c equal to 0.5, for c equal to 1, there is not much oscillation, but c equal to 0.5, there is more oscillation here. Okay, that is the way we get. And coming to McCormack scheme, and McCormack scheme, as we have done last time, we have to take an intermediate time like ui star. Ui star is equal to uin minus, here for forward difference I am taking ei plus 1 minus ei. And in the next step in corrector, uin plus 1 minus ui n plus half. That ui n plus half I take as the average of uin and ui star. And this is backward difference for ex. Okay, this is the way we take. Same way as we have done for the linear one, here non-linear one. Only thing is here at the in the place of e, you have to substitute u square by 2. That's the only thing. Okay, so the remaining thing is just as it is. So here there is no problem, as I told, because we are taking old values. It doesn't matter even if I take u square there. Okay, so when I do that, we are going to get for McCormack scheme, this is the way we are going to get. And next, another scheme which is called as beam warming implicit method. Okay, so these equations, okay, I will briefly do it. Okay, here I take ui n is equal to, sorry, ui n plus 1 is equal to ui n plus delta t ut plus delta t whole square by 2 utt, etc. And ui here un plus 1 minus delta t ut. Okay. If I take like this, and I subtract one from the other, and ui n plus 1 minus ui n, if I take this is 1 and this is 2, so 1 minus 2 if I take. So what I'm going to get is on the right side ui n minus ui n plus 1. And here it will become 2 delta t ut, and these terms will get cancelled, and it is going to become 2 delta t whole cube by 6 ut. Like this I will get. So if I take uin plus 1 this side and uin this side, so 2 uin plus 1 is equal to 2 uin plus 2 delta t ut plus 2 delta t whole cube by 6 ut. And this 2 can be cancelled. And here ut and utt, I will substitute from the original equation. Ut equal to minus ux, utt equal to minus a cube ux. Right.
Hello, sir.
Yes.
Sir, how are we adding the two derivatives and saying it is 2 delta t ut? But there are different points, no, sir. Like the second equation is written.
Yeah, that's right. That's right. Sorry. Actually, here delta t ut n plus 1 here. Actually, UTN here. That's right. Thank you. So here it will become like delta t into, right, very good, n plus 1 plus UTN. So like this you will get. So here minus EX n plus 1 plus minus EX n will be there. Okay, like this. Just I will show you that. Yeah, this is the way. UIN plus 1. If I divide by the 2, here 1 by 2 will be there. So not this. Yeah. Because these two are not same, here 2 will be there. So half into this side will get. So UIN plus 1 is equal to UIN plus half into dou U by dou T IN, dou U by dou IN plus 1. This is nothing but dou E by dou X IN, dou E by dou X IN plus 1. Okay, so this is the equation I get. So these all the steps I have written, and this is the way we get. And here En plus 1, because here En plus 1, what I have to do is En plus 1 is equal to En plus delta T Et, etc. So this delta T Et, I have to write dou E by dou U into dou U by dou T. And this is Jacobian again, and this will become minus Ex. Okay, so like that I have to write. Here En plus 1 is equal to En plus dou E by dou U into dou U by dou T is this. Dou U by dou T, I write it as Un plus 1 minus Un by delta T, like this. So dou E by dou, this I want, dou E by dou X n plus 1 is dou E by dou X n plus dou by dou X of this. Okay, so dou E by dou U is A. Okay, so like this I will get. And then I have to do this derivative again. Previously we have done that, right? So dou by dou X of A UIN plus 1 minus A UIN. Here we will write A second central difference UI plus 1 minus UI minus 1 because dou by dou X is there. And wherever UI plus 1 is there, I have to write AI plus 1 and AI minus 1 here, like that. So this is minus UIN dou by dou X. So I will get AI plus 1 minus AI minus 1, like that. So this way, if you substitute and simplify, you are going to get this equation. And this is again unconditionally stable and order of accuracy delta T whole square and delta X whole square, just like Lax-Van-Droff and McCormack scheme. But here, this is also a second order accurate scheme. And if you apply this particular beam warming scheme, I'm going to get, this is the oscillation I'm going to get because of the dispersion error. You can see the error is so large as the time is increasing. So I am marching in time at 0 seconds and 0.6 seconds, 1.2 seconds, and 1.8 seconds. The oscillations are increasing. You see the actual signal is only this much, and the error is going. And few more time steps, it is going to increase so much. And though the actual signal value is 1, the error value may become more than 2 or something. So which is not preferred. And because of this, I have to add some artificial damping. Okay, this artificial damping is like this. So this is like so I add, so this can be explicit or implicit. Explicit damping will be added on right hand side, and this will be added on left hand side. And this explicit damping will be like this: epsilon E delta X power 4 dou to the power 4 U by dou X power 4. And this will be epsilon I delta X whole square dou square U by dou X square. I will talk about this implicit later. So this one, when you take, so this epsilon e and dou power 4 u by dou x power 4, if I expand, I am going to get ui plus 2 minus 4 ui plus 1 plus 6 ui minus 4 ui minus 1 plus ui minus 2 by delta x power 4. So into delta x power 4 is there. So this gets cancelled. So this is the one I'm going to add epsilon e into something like this. Okay, this is added on the right hand side. You write the finite difference scheme and add this particular term on the right hand side. And this is called as damping coefficient. And again, it is applied to you and how much damping coefficient you have to give by numerical experimentation. You have to find out what is the best one. Like I told you, over relaxation factor, right? So how much you have to give, it depends on the problem. So here also, this is problem dependent and you have to find out. So this is the term which is added explicitly on the right hand side like this. Okay, this is the particular term that is added. So when you add this, previously I have, this is the solution I am getting. And by adding that, I am going to get this type of solution. You can see how much it got damped. So only a small oscillation is there. And that bigger ones, everything is absorbed. Okay, that is diffused. So solution of the inviscid Burgers equation by Weir warming implicit method with damping epsilon e equal to 0.1 and delta x is 0.1, delta t is 0.1. So in that way, if I take, so this is going to be the solution. So that is the advantage of damping. Sometimes this is called as linear damping. So artificial damping, linear damping, numerical damping, all these terms are used. And okay, so I will talk about that again. Two more schemes I am going to discuss. Explicit first order upwind scheme, right? So forward time, backward space. It is just simple forward time, this one, and backward space, EA minus 1n. Okay, this is the way. Only thing again, in E place of E, you have to put U square by 2. Then this completes the scheme and you are getting a nice behavior because it is first order accurate upwind scheme. And implicit first order upwind scheme is there. Okay, so where I have to use n plus 1 here. ui n plus 1 whole square and ui minus 1 n plus 1 whole square. Here, this is problem. Okay, because this is unknown square, this is unknown square. So here I have to use some method of linearization, that is lagging is used here. So instead of u square, u unknown square, I do uin into uin plus 1, old value into new value. Similarly, ui minus 1 n into ui minus 1 n plus 1. So when I have like a n plus 1, b n plus 1, so I will write a n b n plus 1. So one new value, one old value, one new value, like that I put it. So this is lagging. Okay, so that is the way it is done here. uin plus 1. Okay, so this is unconditionally stable and order of accuracy first order only. And this is the way it behaves. Okay, so now I talk what about that artificial damping or linear damping. There are some terms, some points we will see. Addition of a fourth order damping term. So here we are adding something, means I am introducing some error. But as I told, the term that I am adding is very, very small. For a second order accurate scheme, I am adding some fourth order term, which is of negligible effect on the solution. But it damps. Addition of fourth order damping term to a second order scheme does not affect the formal order of accuracy of the algorithm. So this is important. And fourth order damping terms are generally added explicitly, right? That is, they are added on the right hand side of the equation. Therefore, as mentioned previously, stability analysis will impose an upper limit on the value of damping coefficient. It is then clear that when performing computations by now, so what happens if you do implicit schemes? If you do implicit schemes, what happens is naturally the person who is using the implicit scheme is tempted to give large delta t. Okay, so when large delta t is given, there will be large oscillations will be there. So this explicit damping may not be sufficient to damp those errors. So at that time, we use what is called as implicit damping. It is then clear that when performing computations by implicit schemes where large step sizes or correspondingly large coherent numbers can be used, the amount of adding damping may be insufficient to damp out the oscillations. To overcome this limitation, a second order damping term is added on the left hand side of the equation, in addition to the fourth order damping term on the right hand side. That explicit damping term will be there on the right side, but an implicit damping term I will add on the left side. So now here we have to be careful because I should not lose that tri-diagonal matrix. So an implicit method. So what I'm going to have on rearranging is I am going to get some ui minus 1 plus something into ui plus something into ui plus 1 is equal to right hand side. Okay, so that I'm going to get a tri-diagonal matrix. And to this, on the left-hand side, I'm adding epsilon I, delta x whole square, and uxx. So this is nothing but epsilon I, delta x whole square into ui plus 1 minus 2 ui plus ui minus 1 by delta x whole square. So this and this gets cancelled. So I am adding epsilon I ui plus 1 minus 2 ui epsilon I plus epsilon I ui minus 1. This is I am adding. So what is that I have to do is I have to modify the coefficients. Okay, something which I got some suppose this is a1, a2, a3 like that. These are the coefficients. I am going to get a1 plus epsilon I plus u I minus 1 plus a2 plus minus 2 epsilon I into ui plus a3 plus epsilon I ui minus 1 is equal to RHS. So I need not change any program also, coding also. Only thing is these coefficients of ui minus 1, ui minus 1, they are to be just added with terms epsilon I here, minus 2 epsilon I and epsilon I here. For the diagonal terms, right, I have to just update them by adding this damping coefficient. Okay, so this is the only thing I have to do. But this introduces more damping, right? And in RHS, here I am going to do the explicit damping. Okay, so this normally put as DI, implicit damping. DE is the explicit damping term. So here for implicit methods, both explicit and implicit damping terms will be added, and explicit damping on the right side and implicit damping on the left side. Okay, so by doing this, I am not going to change much of the code, or I'm not going to lose much of the accuracy. But the scheme works with a little bit of error adding into that. The scheme behaves nicely. Okay, that is the advantage of this damping. So just I should.
Sir, why add both, sir? Like one is enough, no, sir? Second order is powerful than fourth order, right? Why again second order and fourth order, both?
No, the second order damping, because I want more damping, second order term will give more damping. Say the fourth order one, it is a negligible damping only it will give.
Then we can remove fourth order, no, sir. Why are we adding?
Can be removed, but actually whenever implicit damping is used, explicit also will be used on the right side. I don't know exactly, but numerically people do that.
Okay, sir. Okay.
Okay. So the addition of damping terms not only eliminates or reduces oscillations in the solution, it helps stabilize the solution. That is, a solution at larger step sizes may be obtained which otherwise would have been unstable. So if you take large step size, it is going to be unstable, but it will stabilize that. And so in applications where density is being computed, oscillations in the solution may result in negative values of density because of large oscillations. And addition of damping terms could help to alleviate the difficulty. So this is the explicit damping term, which is added on the right-hand side. And this is the implicit damping term added on the left-hand side. Okay, the values of epsilon and epsilon I and epsilon E, as I told, it is completely problem dependent. So if a formulation includes both fourth order explicit damping as well as second order implicit damping term, a typical relation is given by epsilon I is equal to 2 epsilon E. Okay, so by numerical experiments, people found some rough rules, but it is left to you. And upper limit value for epsilon E is 1 by 8 for the beam warming scheme is obtained. So like that, we have to check which value is useful. And in applications where viscous effects are confined to a particular region, so sometimes there may be, now these I am talking about inviscid schemes. But if you have viscous solution, actually the natural viscosity itself will dampen the things. But there may be regions like boundary layer flow where there is viscosity dominant near the boundary layer, but outside the boundary layer there will not be any viscous effect. So there I may have to artificially add damping in the regions where there is no effect of viscosity. Okay, so in applications where viscous effects are confined to a particular region, for example, boundary layer regions, physical viscosity may be sufficient enough to prevent oscillations in that region. Therefore, the damping terms are turned on only in the inviscid regions where formation of shock waves, that is large gradients, could cause oscillations in the solution. So wherever you are expecting large gradients in the dependent variable, right, there you introduce the artificial viscosity where there is no viscosity. Okay, so if natural viscosity is there, that itself may take care of to dampen the gradients. Okay, these are the different points on damping. And one example scheme, this is flux corrected transport, FCT. Okay, so if I take FTCS scheme, UIN plus 1 minus UIN by delta T is equal to central difference UI plus 1 n minus UIN minus 1 by 2. So because this is second order accurate scheme, so we here a damping term is added here. So no. This is the Lax-Van-Troff scheme. Sorry, this is Lax-Van-Troff scheme. Lax-Van-Troff scheme we get like this. Okay, UI plus 1 minus UI n minus 1 by 2 and C square by 2 UI plus 1 like this. This is the Lax-Van-Troff, second order in time and second order in space. So here to add the damping, here this is added here, second order damping. And after adding, here it is still like predictor corrector. Okay, this is a scheme called as flux corrected transport. So I'm adding damping and I wanted to remove that damping. So in the predictor, I add this damping term. In the corrector, I subtract this damping term. So UI star, it is given like McCormack scheme, some intermediate one, UI star is equal to UIN minus, this is this term, it is there. And here I am adding epsilon here to C square by 2 because this is also second order accurate. Sorry, second order derivative. This is also second order derivative. So I am adding epsilon 1 plus C square by 2 into this. Okay, so this is adding of damping term in the predictor step. In the corrector step, so I take UI n plus 1 is equal to UI star minus epsilon 2 into all these new values I subtract here, UI plus 1 star minus 2 UI star plus UI minus 1 star. Okay, so this is the way, this is called as flux corrected transport. Okay, so this is one particular method. Again, there are so many schemes are there. It is left to you which scheme you feel comfortable or whichever scheme practically applicable for a particular application. You have to check and use that. So the solution of the wave equation by the Lax-Van-Troff scheme with flux corrected transport, I am going to get this. This is for the first problem, linear problem. It is applied here like this. So this wave nicely moves, right, like this. Though it is second order accurate scheme, you don't see much oscillations here because of that damping, adding damping and subtracting damping. Okay, so these are the things which I wanted to discuss. And some more things are there in hyperbolic solver. I am not going to discuss that. We stop here, the hyperbolic solvers. So there is what I called as the TVD schemes, total variation diminishing schemes, and Runge-Kutta methods. These two are explained in the textbook in Hoffman, and I am not going to cover that. We go to the next chapter. We stopping this hyperbolic solver here. And next class, I will demonstrate these different schemes, parabolic solvers and hyperbolic solvers, which are written in MATLAB by me. So I will just show how they work and how the solutions are. Any questions here?
Sir, that Umax delta t by delta x is there, no, sir?
Yeah.
The condition.
A
Is that
delta t, that is delta t by delta x, not delta
yeah,
x.
delta t by delta x. But
Okay.
should we call it current number or is it some other number?
No, current number only, because current number is defined as A delta t by delta x. Here
Yes.
A is not there.
Hmm.
So it is similar to current number only, but we will not say, I think, current number.
And sir, in case of oblique shocks, this solvers will work. But in case of normal shocks, like flow changes from hyperbolic to elliptic, right? Suddenly, then they won't work, right? Whatever we discussed till now.
No. As I told here, when we are solving shock waves, usually we take unsteady equation, which is parabolic in nature, right? It is
Yes, sir.
parabolic throughout, whether it is supersonic or subsonic, and we march in time, right? So this problem we will not get there.
Okay, so this is not the way to solve a shock
Not like
equation.
hyperbolic solver. It is like a parabolic solver.
Okay, okay.
Okay.
Hmm.
Okay. So if everything is okay, we'll go for the story. And here we take another personality. He is Honda. I think all people are familiar with Soichiro Honda, and Honda name itself you are very much familiar. But as I told many times, all these biggest success stories, they start with very low level. So he is born to a blacksmith and a weaver. Soichiro had an innate passion for machinery. The story of him chasing a car that passed by their town when he was very little has been a topic in many of his interviews. He said that the smell of oil was one he could not forget, the thrill unimaginable. So that is the passion. Okay, as I told, always the drive must be a passion. So if you have the driven passion, so what happens is, even if you uh, get failures or setbacks, you will not lose energy and spirit. Okay, so why people work even after many failures is they don't see them as failures. As I was telling about Edison, so he tried for a material and 1,000 times he failed, but he says, I didn't fail, right? I tried with them and I found that these will not work, and I don't consider it as a failure. In that way, whatever these people try, even if they fall, they find that it is a step for progressing. Okay, so as he was growing up, his father's bicycle repair shop. So his father has bicycle repair shop, and it has enriched Soichiro's interest in the craft and enhanced his tinkering capabilities. So when he is doing repairs and all, so he got a lot of practical experience. And his devotion to technology was only empowered by the country's sudden shift from agriculture to that of manufacturing during this time. So it is like industrial revolution. Soichiro Honda grew up puzzled by the world's development and found his own way to understand it. At 16, his knowledge of machines and his dexterity in handling them were beyond his years. School no longer appealed to him. He wanted practical education. He opted to halt formal training and rather apply as an apprentice in one of Tokyo's automobile servicing companies. And he worked as a mechanic apprentice for Art Shokai in Tokyo. The company serviced cars needing repair and maintenance. It was a difficult time for Soichiro. However, as apprentices were not paid wages. They are merely given a bed to sleep in and food to eat, nothing more. But this did not deter his yearning to learn, though. He closely studied each vehicle rendered to his care. He was very competent in maintenance and repair. He was able to devise ways to simplify elaborate repair procedures and shared this with his co workers, making their jobs easier. Later, he developed a flair for invention. He used it to automotive he used automotive tools and parts in an uncanny manner. He was as creative as he was analytical. He was also just a young boy. He spent his spare time reading motorcycle magazines and committing to memory each detailed description he read. He also closely followed international motorcycle racing. No long after beginning the apprenticeship, he actually seemed educated in the field. His efforts were rewarded as Art Showcase management took notice of his capabilities. The owner then took it upon himself to teach Soichiro everything else he knew about the trade, not only about machinery, but mostly about the business. He was also a very valuable asset as the company used his abilities when they ventured into manufacturing cars. And Soichiro was able to produce quality spare parts from unconventional sources and through unorthodox means. Soon thereafter, Soichiro's rise through the ranks were unstoppable. As Art Shokai ventured into racing, he was named accompanying engineer, and later he was given full independence to manage Art Shokai's branch near his home. He was only 22 at the time and became very successful. He became the most sought after mechanic in the region. And his involvement with Art Shokai ended when he intended to expand the company's undertaking into manufacturing. He wanted to manufacture piston rings, but the management saw no benefits in the venture and shot his idea down. To pursue his dream, he left Art Shokai, so he left the company and started his own business in manufacturing piston rings. Due to the complexity of the material, he had to go back to school to have in depth knowledge of the metals. After long days of making piston rings and long nights of studying and a lot of adjustments in between, he seemed to have achieved his dream. Soon thereafter, he rising through the ranks was unstoppable. As Art Shokai ventured into racing, he was named accompanying. Sorry, this is again. He was finally able to make quality piston rings and supply Japan's automotive giants, including Toyota. He was in a role with his manufacturing business until the war broke out. See things how it turns out. The company was taken over, and his position as president was reduced to that of an operations manager. Most of the male employees were drafted into military, which left Soichiro with women in his rank and file. He made certain adjustments in the manufacturing process, making it easier for the women to comprehend and perform the tasks. The company functioned smoothly, nonetheless, until his building containing the piston rings and all machinery was destroyed during the bombing raid by American warplanes. At the time, bombing time, his industry is gone. And he lost most of his investments. The few he salvaged after the war, he sold to Japan's big companies to be able to get back onto his feet. The broken country did not break his love of the automotive industry. However, nor did it break his spirit. From the rubble created by the war and the country's need for practical motor vehicles rose the Honda Motor Company. So he started his company. And he pursued his dreams of manufacturing motorcycles. The first Honda motorcycle, literally an engine connected to a bicycle, was made in 1948. Further developments created useful and efficient machinery that catered to the people's needs. Within a decade, Americans had embraced the idea of Honda motorcycles, and shortly after, Soichiro creations were winning international motorcycle races. And his automotive line was not as widely accepted as his motorcycles were. The Department of Trade at the time discouraged Soichiro from getting into car manufacturing, as many had done so, and they were already quite successful at it. There was no place for another startup company crowding the markets. Still, he continued working on his prototype and created a small yet efficient and sturdy model fit for the times. He was given permission to proceed and build competitive empire, and he did. And he said, success can only be achieved through repeated failures and introspection. So this is important point. His journey was long and difficult, his life full of trials and challenges. Several times he was shot down, and several times he stood up to continue what he loved doing. At no point did failure prevent him from pursuing his dream. Failure only urged him to find a way to do so and heightened his need for learning. He used his love for automobiles, his knowledge and skills to pursue his dreams. And despite the obstacles, he fought within reason to achieve his dreams. And today, the company manufactures motorcycles, cars, and even marine and aerospace parts and equipment. And his innate characteristics were embedded in his company. Being creative and giving the consumers what they need sets the company apart. Also, creating a machine and studying it find ways make it better was a virtue he passed on. And most importantly, having a patience to seek each task thorough was necessary. Honda is now one of the leading automotive manufacturers, and the company's motorcycles are still winning races around the world. And he enjoyed the benefits of his hard work and diligence until his death at age 84. So he says, instead of being afraid of the challenge and failure, be afraid of avoiding the challenge and doing nothing. If you hire only those people you understand, the company will never get people better than you are. Always remember that you often find outstanding people among those you don't particularly like. Okay, so these are some business secrets of him. Okay, thank you. This is the success story of Honda.